All right, this is DES, lecture number 10. Okay, what's DES? Where did the name come from? Anyone remember? Anyone know?
The name Dez? I can't remember.
Come on. Is no one reading that awesome book? How could you not read that book? It's like amazing. Okay, I go to the gym every morning, and that's the only place I read. See, I'm reading Spam Nation right now, which is amazing, by Brian Krebs. That's amazing as well. But you need to read it, because you guys will be acing all this stuff, because that's where I'm getting a lot of these bonus questions stuff from. But okay. So, secret and public key encryption systems. Okay, we already know this. This is nothing new. Okay, you saw this on the last test. You'll see it on the next test. Okay, you all know how this works, don't you? Which one's faster, the symmetric or the asymmetric? Symmetric is always faster. Okay, yeah, this is nothing new here, so just make sure you know this. Okay, secret key are symmetric. DES is one of them. There's also EES, there's skipjack, there's AES, there's a bunch of other ones out there. We have a single key. So me and Austin want to communicate, we have one key between us. We have the issue of key management, key distribution, all that kind of stuff, but it still is an issue. Okay? All right? It's good as long as the key is kept secret. If either of us was to release the key, obviously the whole thing's out there. So again, nothing new at this point. Okay? All right. So there's some problems with them. Revealed keys. Obviously, if the keys are revealed, we're out of luck. Okay, makes sense. Okay. Key distribution, like I said, I got to get him the key, and he's across the country, so how do I get it to him? That could be an issue. There's also a large number of keys involved. If I want to talk to Austin, that's one key. If I want to talk to Matthew, it's another key. And if I want to talk to Sam, it's another key. If Sam wants to talk to Matthew, it's another key, and so on and so forth. We end up with an awful lot of keys. Okay? So, it says a decree went throughout the land to find a good, secure algorithm. Okay? IBM basically did it. They came up with the Lucifer cipher. Okay? And it was called Lucifer. I think I put it in here. Actually, I did. I put it in here. We'll cover it. Okay? It's a cipher based on what's called the Feistel structure. Okay? Horst Feistel did it. It's a symmetric structure which encryption and decryption are nearly identical, just manipulating the key sequence. So, pretty much the same to encrypt and decrypt. We will not be walking through the entire algorithm in your homework assignment. No. Won't. Okay? It's based on the Lucifer cipher. Why was it named the Lucifer cipher? Well, the reason was not because it was like a devil. It was based on the demon algorithm. Okay? Demon, devil, Lucifer. Okay? But really, it was short for the demonstration algorithm. When they made it, it was originally they called it demonstration to show it. But the length of the name had to be shortened because in a lot of languages you're limited on length. So they had to get it down to 5 letters. So that's where the demon came from. So really, it was demonstration. It wasn't anything to do with the devil. So kind of funny. Nothing to do with the devil at all. It was all because it was written in APL and couldn't handle the length. Okay? All right. So let's talk about DES now. Okay? 1977, NIST went out and said, hey, we need something, and they came up with this for general use. It was accepted worldwide as a standard. It was for quite a few years. It worked very well. It's actually still used today. It's really used today in triple DES, which is encrypt, decrypt, and encrypt. But it's still a form of it is still used to this day. Okay? There are hardware and software implementations. Which one do you think would be faster? Hardware or software?
Hardware. I think it's hardware.
It's hardware. It's always hardware. Because it's dedicated for one task. Think of software like it has to run on top of another system. Now, obviously, hardware does run software. But really, we're talking dedicated hardware system or no. So hardware is always faster. Okay? Here's what the algorithm is. A complex combination of substitution and transpositions. Starts with a 64-bit plaintext block, a 56-bit key, 16-round algorithm, and the same algorithms used for both. That's what it is. Okay? Now it gets confusing. Okay? So far, so good. We're all here? All right. Here's what it looks like. I don't particularly like that picture whatsoever. So we got a different picture, which I will show you. Okay? We're going to see there in a second. The algorithm, it basically uses what's called initial permutation. We do something to the data. Then we have 16 cycles to do something with it. Then we inverse what we started with. That's all it is. And that's what the other picture kind of showed, but it was hard to see. Here's what the cycles are. So I said we do something initially, then we go through 16 cycles. The 16 cycles, basically we take the 64-bit, split it in half. So we have two 32-bit chunks of data. We only work with the right side, okay? So we take the 32-bit on the right side only, expand it from 32 to 48. You will see how all this happens. Then you XOR it with the key that's manipulated, which you will see as well. Then you have what's called the substitution or the Sbox, okay? The 48 comes back down to 32. Then we have the permutation of the P box on the right side only. Then we mix it back with the original left side, and we're pretty much done. Okay? Then we concatenate them back together. So we're going to walk through each one of these sections, because right now it's like, huh? What does that mean? So I will show you. Okay? Your homework involves the initial permutation and expansion permutation. That's about as far as it goes. Okay? Pretty simple. Okay. All right. So here's what happens. We take our input data, which is how many bits? 64. Then we cut it in half to 32s. So our initial input is 64 bits. We come in, we do something to it, which we're going to see here in a minute. That's in the initial permutation. Then we split it in half. The left side we don't do a darn thing to. The right side we do a bunch of stuff with it. A copy of the right side becomes the next left side. You follow me here? So what happened was we separated it out. Here's our 64 bits. We divided it in half. We got 32 for the left, 32 for the right. We don't do a darn thing to the left. The right side, a copy of the right, becomes the next left.
Before anything's done.
Right, before we do anything. Okay, so a copy of the right becomes the next left, but then we take the other copy of the right, and we go through the substitution box, the permutation, then we XOR it back with the left side, and that becomes the new right side. Okay? So then again, we take a copy of that right, and that becomes the next left, so on and so forth. We do that 16 times. And then we undo what we did initially, and we're done. Pretty simple. Okay. All right, here's the initial permutation. You take the bits and just move them all around. Anyone ever play Spirograph when they were young? Is anybody here old enough? Yeah, you remember it. You probably had one too.
Yeah.
Okay. It was awesome. You take this thing and you just take your pen. It was awesome. But no, we don't have that anymore. What happens is bit 1 goes to position 40. Now your homework assignment is very critical. You read the instructions because it's actually using the different table. But just follow the instructions on it. But the way this works is bit 1 goes to position 40. Bit 2 goes to position 8. Bit 3 goes to position 48. Bit 4 goes to position 16. So we're just moving them around. So whatever was in bit 1, we copy it into position 40. Everybody see that? Whatever is in bit 2 goes to position 8. So on and so forth. Easiest way to do it is make a bunch of boxes. Like 64 boxes. And so you have, go in Excel, make 2 sets of 64 boxes. Have the data, what you're going to start with, I'm going to give you the data up on the first one. Then when it says 1 goes into 40, take a copy of 1 and put it down in 40. It's not hard to do. Okay? Now for this assignment, there's a sample up there. Make sure you do the sample. And for AS as well, you must do the sample. You're really going to screw yourself up. Okay? All right. The final permutation is the exact opposite. It's undoing it, and this is actually the one you're working with. So we really got the final as the initial, but it's still the concept is the same. Okay? So really, if you notice here how 1 goes to 58. What happened to 58 there?
Goes to 1.
See how it's the exact opposite? So if you look down at the bottom row, 58, which is the second column, 58 goes to 1. You see that? Then if you look at the final permutation, 1 goes to 58. So it's the exact opposite is what it is. For the assignment, you're actually working with this one, though. So just make sure you use the one on the assignment. Okay? And I have a sample up there. Make sure you go through it. All right, now here's the cycle. So left side, again, we didn't do anything with the left side. The right side, we expanded it from 32 to 48. Then we took our key. Our key is 56 bits. We took our key and we actually shifted each round, which you can see here in a second. Then we take that 56-bit key, bring it down to 48. XOR our right side, which is now 48, with our key, which is now 48. XOR those together. Then run through a substitution with an Sbox, then a Pbox, and then combine them back together. We're going to see each one of these steps here in just a second. Okay? All right. Here's what the expansion permutation does. Bit 1 goes to bit 2. Bit 1 also goes to bit 48. See that? Look at bit 1 up here on the top left. This is bit 1. Bit 1 gets copied down to bit 2, but it also gets copied all the way over here to bit 48. So that one bit is now in 2 positions. That's how we're going to expand from 32 to 48. Okay? And this is an easy way to see it. So bit 1 goes to 2 and 48. Where's bit 2 go? 3. Bit 3 goes to 4. What about bit 4? 5 and 7. So you see some of the bits are actually getting expanded. So that 32 bits is actually becoming 48. Y'all see that? Easy enough to understand that? You have to do this exact table on your assignment. So whatever's in, so you have a block of 32, then you just expand it. Okay? Now on your assignment, I actually give you 64 bits. Which bits go through the expansion permutation? Let me back up a couple slides here. The right side. So remember, initial permutation used all 64. But we only expand the right side. Everybody see that? Everybody should see that. We're not expanding the left side. Remember, we had the initial permutation, which was back 18 pictures ago. We had the initial permutation. That was 64 bits. We mixed it up. Then we took that 64 bits, divided in half. We got the left 32 and the right 32. The right 32 is the one we expand. Do not expand the left. The good thing for you guys, though, is if you do expand the left, that answer is also on the quiz. So you're like, oh, the answer matches. Well, yeah, but the answer matches wrong. So, because I expect you to do that. But if you do it correctly, that answer is there as well. So it's one of those things. You ever do a quiz, you're like, ooh, I got the same answer. It must be correct. It's not always correct. You have to know the correct way of doing it. Okay? Is everybody okay? We are expanding what side?
Right.
The right side. So bits 33 through 48, 33 through 64 actually become bits 1 through 32. But it's really just the right side. So bits 1 through 32 are the left side. 33 through 64 are the right side. So when I tell you, where's the expansion? Oh, it's up here, the other way. So when I tell you bit 1 goes to position 2 and 48, what's bit 1? It's really bit 33. Y'all see that?
Yeah.
Because remember, we started with 64 bits. Right, we don't do anything with the first 32. So really, bit 33 is actually bit 1. Everybody see that? So bit 34 is actually bit 2. It's going to get some of you still, I guarantee. And I don't think I've ever explained it that way in the lecture before. But You understand what I'm saying? The right side is what we expand. So bit 1 is really bit 33. Okay? All right. So now let's talk about the Sboxes, the substitution choice boxes. Let's see what they do first. Let's go back a couple pictures here. What do the Sboxes do? We're talking below that thing in the middle here. This thing right here is actually taking the 48 bits. Remember, we had 48 from the expansion. We had 48 from this key. We XOR them. Then we end up with 32. Do we know what an XOR means? Have we even talked about that yet?
No, I was going to ask you, what is XOR?
Okay. That's a good question. XOR is one or the other, but not both. So if I have 1 and a 0, one or the other. So if 1 is true and 0 is false, okay? So if I give you a 1 or a 0, what's the answer? True or false? That's true. It's 1. What if I give you a 0 or a 1? It's still true. Okay? But with an XOR, it's one or the other, but not both. So if I give you 1 and a 1, you get a 0. If I give you a 0 and a 0, you get a 0. So 1 and a 0, you get a 1. 0 and a 1, you get a 1. But one or the other, but not both. Okay? See, an OR is one or the other. Makes sense. That's why I'm getting a bunch of people emailing me, is it this or this? I always answer with the word yes. Someone emailed me, who's Chad? Chad in here? No one's going to admit to it. Chad said, is it this or this? So I said yes.
Or is this or this?
You see, I mean, think about it. If you give me two choices and if either one of them is correct, the answer is yes. Is that not the correct answer?
It's true.
So don't ask me any more question. Because I always answer you with yes. And then you're like, well, which one was it? Well, you didn't ask me that. You just asked me this one or this one. Yes. That's life. So don't answer.
We can ask an XOR.
Sure, then you can ask me, is it this? The answer is yes or no. But if you ask me, is it this or this? Is it right or wrong? Well, yes, it's either right or wrong. Yes, that's the true answer. Okay, my algebra teacher in high school did that to me. I still remember it to this day.
Is that why you're passing it on?
Actually, Dr. Schnoy does too. A lot. But if you seriously think about it, so we'll pretend the answer to the assignment is 5. And if you came to me and said, is the answer 5 or 8? Yes.
So the best way to put the question is, which is correct? 5?
No.
Yeah.
8. Leave the whole order out.
Well, see, he asked the which is correct. That's okay. Okay? But if the answer was 5 and you said, is it 5 or 8? The answer is yes. So just remember that if you send me an email. All right. So expansion permutation, we know bit 1 is actually bit 33, because 1 through 32. Perfect. Okay. And so on and so forth. Okay. Now the Sboxes, so we're going to take 6 bits and shrink them down to 4 bits. Remember, we had to go from 48 back down to 32. Because the whole thing has to become 32 again to match up with the left side. So we take 6 bits, bring it down to 4. We'll see how that goes in a minute. But that's, and if you read that book, which, believe it or not, y'all are too busy, I guess, they'll tell you they really don't know why they did this. They're like, what was the thought process behind it? And they think there's actually some flaws in it, is why there's some issues. But okay. Here's the Sboxes. They tell you where each bit goes, what to do with that. Okay? And you'll actually see, okay, no, it's not on, I think it's on another slide.
So
Yeah.
it's like a template for letting you know which bit goes where.
Right. Right. Okay, then we have the P, or the permutation choice box. Here's what that goes. They're just moving them around. Yet again. Okay? All right, so we've looked at all those. We really haven't looked at the key much yet, but we've looked at the expansion, we've looked at the S box, and we've looked at the P box, correct? Okay? The key, if you notice up here on the top right, it says the key is shifted. Okay? So imagine a key, a set of bits. Okay? Cycle number 1, we shifted by 1 bit over. Cycle number 2, we shift it by 1. Cycle number 3 through 15, we shift it by 2. Then cycle number 16, we shift it by 1. Just what it does. So it's just the key. Imagine, rotating the bits around, moving them one at a time. Okay? All right, here's the permutation choice. Now this is right up there at the top under the key, where it says permuted choice on the top. Remember, we had to go from a 56-bit key down to 48 bits. We're talking right up in here, because remember, this is the shift area. But we got to take that 56 bits from our key and bring it down to permuted choice. Okay? Bring it down to 48-bit. So we just drop off a few bits. Hopefully that wasn't the important ones. You'll see some of the bits just go away. Okay?
So you break the key in half as well?
Yes. Well, yeah, pretty much yes. Yep. All right. So the DES algorithm, again, I already told you how it works for encryption. So the left side is actually the prior right side. Do you agree with that? Because remember, the left side comes down, then the right side becomes the next left. So the way you read that is the left side is actually the right side minus 1, or the prior right side. Okay? So the right side is equal to, so the next right side is actually the left side XORed with the prior right side ran to a function with the key. See how I read that?
A little plus thing is XOR.
Right, that's the XOR, yes. I couldn't get a better XOR symbol in there. Okay? We're not going to go through each one of these. Decryption, it's pretty much the opposite. Okay? If you look at it, it's opposite. For the most part. Okay? All right, keys are submitted in reverse for decryption. All right. Some issues. I would definitely make sure I know some of the weaknesses of this for sure. Okay. Secrecy is the rationales of the Sbox, Pbox, and key transformation was not released. Don't know why. To this day, we still don't know why they came up with that. It literally could be them deciding to someone just pick a number. There was a movie out there called Beautiful Minds with Russell Crowe. Anyone seen that movie?
Yes.
Okay. If you remember, it's like three-quarters, the guy was kind of freaky in the head. Three-quarters of the way through the movie, he's proven some statistical stuff. And he's saying, he's like, these numbers are wrong. They're wrong. And all of our statistical research is based on these numbers, and they proved that the guy who came up with all this stuff just picked them. They weren't based on any actual stuff. He just picked them. So how do we know that the person who made the S-Box didn't say, hey, Austin, number between 1 and 8? They might have done that. He said 3. Okay, 3. Okay. Now, Matthew, we need to match it up with another bit between, 12 and 85, or, whatever. It's just, you don't know. So we don't know that answer. Okay. Design flaws is NSA released information about the S-Boxes. No S-Box is a linear function of its input. Then we have diffusion. It says changing one S-Box changes at least 2 outputs. In other words, if you change 1, it's going to affect at least 2, which is good. Okay. But the S-Boxes were chosen to minimize differences between the number of 1s and 0s when a single bit is held constant. So what they're talking about, so if the first bit is always a 1, they want the S-Boxes to manipulate that, to make it change. But y'all know what random is, don't you? Random should be just a random number. But doesn't it sound like they're manipulating it to make it more random?
Well, every random number generator
It's on the seed anyway.
Yeah.
Right.
Nothing's actually random.
There's no
Give me a number,
true
give me a number,
random
give me a
number.
Give me a number. That might be random or
Right.
considered random. But
Even if I was to just randomly pick someone in this room, my thought process is, I know certain people more. So I would probably, pick on them like I know Matthew. So I would probably pick them more, okay? Sam for getting the only bonus. So did you read the book?
I'm on page 32,
Okay. But how do you know that answer?
because I have the book. I was like,
Okay, yeah. So, all right. It's actually at the very end of the book. That's where they really get into in depth about that. But
I've got
okay.
20 seconds left. I got there, but
I was like, wow, because a lot of you put give him a name. A whole bunch of people said the same name that was wrong. All right, but okay. But see, so okay, let's continue on. We're not going to get anywhere. The number of iterations are 16 cycles sufficient, or are they too many? They're saying 8 cycles should be enough. Okay, I used to work when I was in the military with a guy who was a blackjack dealer from Vegas. This guy was good. I mean, he would literally take a deck of cards and shuffle them. Then he would, take the deck of cards and he'd grab the top card and says, "See this card?" It's a whatever the card is, and he'd hand it to you. You never got it. It's impossible. It's like, God, I don't know how he did it. He'd literally take the card, show it to you, then hand it and you grab it, and you never get it. You always get some other cards. Like, because he was really, really good. But the point is, how often do you shuffle cards? Now, they're saying after 3 shuffles, cards are pretty much mixed. So after 8 cycles, Dez is pretty well mixed. So why did we do 16? Make it sound better?
Be sure.
Yeah, to make it sound better. But maybe the second 8 is making it worse. There's got to be a sweet spot on where you should stop. All right. Brute force, it says Lucifer has a 128-bit key. Dez has 56-bit. You'll have to figure out why they lowered it. There's a big old story behind it. Okay, 10 keys per second would take 228 million years. 1 key per whatever would be 2880 years. Basically, they proved it could happen. Okay. January 1999, Dez was broken in 22 hours and 15 minutes using a deep crack machine and 100,000 PCs. Checking 100 or 256 billion keys per second. Okay? So, that's still a lot. But, it was broken. And the fact is, once something broken, I'm assuming none of you bought a Pentium 66?
No.
Well, I bought one. Because obviously I was around that time. I was alive then. I remember buying one. It was the same time AMD was coming out with something. I forget what it was at the time. So I bought one, like everybody else did. And as soon as we all bought one, what had happened was IBM pushed it out with a flaw. It was a floating point error. It's like the 4 billionth position would be off by 1 on this really obscure calculation. But the point is, there was a flaw in it. So everybody knew there was a flaw, and the moment there's a flaw, even though the flaw is not going to affect you, you want a new one. I got one of the first iPhone 6 Pluses. Did you know there's a problem with the camera? Certain phones can have blurry pictures. I don't have blurry pictures, but I have one of the phones that supposedly is affected by it, so they replace it for free. But it's like, well, why would I? But since I know it has a flaw, should I replace it? But the flaw is not affecting me, so should I replace it? It's one of those things. If it's not affecting me, should I replace it? So, NSA will no longer certify Dez, yet it was still a pretty good algorithm. Okay? All right, let's continue on. So weaknesses. You need to know this. Positively need to know these. They will be on the test. Okay, complements. Okay? Basically, we're saying, a complement is the opposite of something. Okay? So if you use Dez with some plain text and a key to get some ciphertext, then the opposite of the plain text and the opposite of the key will give you the opposite of the ciphertext. It's a problem. I mean, it's not a serious problem, but it is a problem. Okay? Weak keys. Certain keys out there could, first of all, occurs when each key consists of only zeros or ones. First of all, who's going to create a key that's all zeros or all ones? That's stupid. But the point is, if you do that, it could cause a problem. But, what's the most common password? 1, 2, 3, 4, 5, 6? Seriously? What the president of Syria's password was 1, 2, 3, 4, 5? So, come on, it's crazy. Okay? Semi-weak keys. Okay? What they're saying here, multiple keys can decrypt a message. So, basically what they're saying is a different key could also decrypt the message. That wouldn't be a good thing. You wouldn't want different keys to decrypt it. So there's 3 of them so far. You got those 3? Complements, weak keys, and semi-weak keys. Okay. Here's some weak keys. I can see someone saying 0, 1, 0, 1, 0, 1, 0. I mean, it basically just, pick it. It's funny because if you look on my YouTube channel, it says my name now. But you can actually see the name that it was originally registered with. And it's like XYQE8 or something. And people were, for the longest time, before I changed it to Kenneth Dewey, were trying to figure out what the heck that meant. Well, I was just playing around with Google Hangouts, and I had to have a YouTube channel to link it to. So I literally just on the keyboard with my fingers and came up with those letters. So really there was nothing involved in it.
Random generator.
Exactly. But the point is, people could be using these keys and doing it. Okay? Here's some semi-weak keys. And those are bad things. Here's some more weaknesses. Design weaknesses. The expansion permutation repeats first and fourth bits of every 4-bit series. I mean, if you looked at those diagrams, weren't they kind of symmetrical? Obviously, you know something's getting repeated in there. And when you start going through the homework, you'll notice that some of the rows kind of get moved around differently. Okay? So design weaknesses, 2 different but carefully chosen inputs of the Sbox can produce the same output, which it should not do. Based on the theory of diffusion they talked about, 2 things going to the Sbox should never produce the same result. But it can. Okay? Key clustering. 2 more keys produce the same encryption. Again, we don't want that to happen. We would not like 2 different keys. Okay? That's kind of like having 2 different answers for a test. You shouldn't have 2 different answers. But, all right. So in addition to the same, there's also key clusters that do it. Okay, so there's what, 5 now? Is that right? We're up to 5 weaknesses. Differential cryptanalysis is a powerful code-breaking technique. Okay? It says uses carefully selected pairs of plaintext with subtle differences. So I'm going to take my plaintext, manipulate it just a little, and see what happens. That's what they're talking about. Okay? And they were just, figuring out by certain small changes, you can figure out what happens to it. So, all right. All right, that was pretty much it. So, okay. Now let's talk about double encryption. We know DES is considered weak. But back in, years ago, I wouldn't say it was weak. Might be considered weak today. It's not weak back then. Okay? Someone asked me, am I going to get the new iPhone? What do you think? Should I get it or not?
No, it's the same thing.
Pretty much the same as my 6 Plus. Okay? And, they're going to come out with another year, so it's like, do I really want to upgrade? Okay?
Apple's doing a program where if you sign up, you buy a phone from them, you can upgrade like every year.
That's
so
what
they
I'm
know
probably
they're
good. That's the
doing
one
it.
reason I might do it. I just got to go to Apple, AT&T first to find out what happens. But
You should just do Windows Phone.
But see, I bought not a battery backup, but a charger, basically a USB charger, and from Anker, Anker. It's funny because the other day I was charging my phone and my battery backup at the same time through this device. Okay, normally my battery backup takes a full 24 hours to charge. It has about 3 full charges of my phone worth of battery in it. So it normally takes 24 hours to charge. But I was charging that and my phone at the same time. That's how long it took.
An hour or 2 hours.
3 hours to do both of them. I'm like, that's like impossible. The point was I wanted to buy another one for my office, but I was like, wait a minute, I bought the other one maybe a month ago. So is there something better by now? If it's been a month, there might be something better. Well, the same way with DES. DES initially was great. But yeah, over time, like AES is great today, but is AES going to be great 20 years from now? It should be, once we cover it, you'll understand why. But so, it might be weak, but it was still good, okay? So what if we use 2 56-bit keys back to back?
So encrypt the encrypted message.
Yeah, would that be double? So if we took a message, encrypted with a key, then encrypted it again with a different key, would that give us double encryption? No, it wouldn't, because a 56-bit key is 256 possibilities. Is two 56-bit keys 2 to the 112th? Is it? Is that a yes or a no? What do you think? No, it's not. It's actually 2 to the 57th. Because remember, if you look at 2 squared is what? 4. Then 2 to the 3rd, so it's just doubling it. So adding from 2 to the 56th to 2 to the 57th, we're actually doubling it. So it's not 2 to the 112th, it's really only 2 to the 57th. Y'all see that?
Didn't you have a question like that on the test?
You did?
Yeah, I did. The reason I did that is because that lecture was actually moved its position. That's why it was on the first test. Normally it's on the second test. So normally you wouldn't have had that yet. But okay. So it's really 2 to the 57th, not 2 to the 112th. Okay, that's the end of DAS. Let me stop this recording.